Now that we know how the UART actually works and how it utilizes oversampling to transmit or receive data, let's take a look at its overall construction. And in this video, I'll take a top-down approach where I'll show you the whole system, and then in separate videos, I'll actually dig deeper into the different components of the system and show you how they're implemented. But overall, this diagram shows me the whole system, and it tells me that you really need 5 components to actually construct the whole system. And these components are a baud rate generator, which is technically something that ticks every certain period of time based on the baud rate. It's just basically the one that ticks 16 times the baud rate, because the oversampling tells me that you agree about like the baud rate, which is, let's say, 9600 per minute or something like that, or per second, and then you need 16 times that. Really, what I'm trying to say in here is it's just a timer, and that's why I said this is a timer. And we're going to utilize a timer that we've seen before, the one that takes the final value as an input. Okay, so and I'll show you how you compute that particular final value based on the different baud rates in a separate video. But for now, you know that you set the final value, and this one just ticks and provides me its tick to a couple of modules in here. And the rest of the system tells me that the modules are a receiver module in here and a transmitter module in here and a couple of FIFOs, one in here and one in here. And really, this diagram is showing me that you have some sort of a receiver part in here and you have a transmitter part in here. Okay, and what you need to know for now is that the receiver and the transmitter are just finite state machines that take certain inputs, the ones that you see in here like arrows, and it generates certain outputs. The same goes with the transmitter. It takes this particular one as an input, this particular one as an input, this one as an input, and generate this output and this output. And the FIFOs are technically they're the same exact module. We just instantiate a couple of instances of it, so we can use it, one for the receiver and one for the transmitter part. All right, so this is how we construct it. Let me at least walk you through virtually how we actually make this thing work and how to receive and end. So I'm going to start with the receiver port in here. I'm going to show you how it works and why do we need a FIFO in these both parts actually. All right, so let's say for the sake of argument that this particular system here, we're going to take a look at it and say, well, we're going to put the UART in my system. And of course, if you're receiving and sending, you need a transmitter and a receiver. So of course, another system will be connected to its own UART core, and the other system in here will have like its transmit, which is TX connected to the RX in here, and it's transmitting 1 bit at a time. Remember, this is a serial communication protocol. So for the sake of argument, let's say that we want to basically transmit this particular data point in here, whatever that data point, I don't care. And let's say that our UART, for the sake of this example and for the sake of our design, we're going to assume that it sends 8 bits at a time, or a byte at a time. Or, well, it sends the bits separately, but it receives and sends one byte, which is 8 bits. All right. So what we know is this particular pattern will be sent to my receiver or on my RX end 1 bit at a time. And of course, based on the baud rate generator, I'll have that ticks, or my system will be ticking 16 times that baud rate, so I can decide the middle point of that 1 or the 0. And we're going to take that S tick and we're going to give it to that receiver, which is just a finite state machine. So what does the finite state machine do? Well, the finite state machine will just assemble these ones and zeros and so forth. So basically it'll take this 1 in here and then followed by 0, followed by 1, followed by 1, and then you get the point. At the very end, I'll have some sort of an internal shift register that will combine all these 1s and 0s together. And then once it's done, whenever the receiver is done receiving a certain byte, and of course if there's a parity bit, we're going to receive a parity bit in here. In this example, I'm assuming there's no parity bit. But anyway, you receive an extra bit if you want to. Anyhow, so the receiver, once it's done doing that and figured out this data point and received a byte, all it does, it just tells me, well, I'm done. So I've named that signal RX done tick, which is just a done tick for the receiver part. I called it RX because there's a similar one for the TX, so that in our code we don't confuse them. Anyway, what really is happening is the following. So this particular value will be available at the RxD out, and this done tick will actually just tick in here. So let's see what happens then. Well, this particular tick in here is connected to the right port of a FIFO. And the right port of the FIFO have that particular value that we just received. So what I'm really doing is I'm telling you, well, this value will be written to the FIFO, and of course if that FIFO is empty, it will be pushed to the head of the FIFO. And since we're assuming, or let's assume that we are using a first word fall through, that means this particular value will be directly available at the output of that FIFO right away. Okay, of course this tick in here will be just available for a short period of time that allows me to push this new value to the FIFO, and afterwards it will be done. So now what happens in here? Well, this FIFO now have that particular value, and I can read it in here, and I can interact with this FIFO using its read port or the D out, and I issue a read UART, and I can check the empty. So this FIFO has a full flag, but I'm not utilizing it in my system. So the receiver assumes that the FIFO is overflow is available, but I could just append my system or modify it a little bit so to make use of this full. But for simplicity, I'm just going to say, well, the FIFO has enough space. All right. Then, before I move to the transmitter, let's think for a minute, why do we need a FIFO? Well, let's assume that I have a different data point, and this data point in here, let's say 1111 and then 0001, okay? And let's assume that my receiver actually received this data point and then basically pushed it in here. So my FIFO have these two values. So now this is why we need a FIFO here. So what happens is I receive two words, and my system is connected to this particular UART module, okay, but it might not have enough time, or maybe it wasn't ready to receive the data. So what I'm doing is the FIFO creates a storage that makes sure that if a transmitter sent me something, I have it and I'm not going to lose it, and my system or my module can wait till I'm actually ready to read them. And of course this situation happens if the transmitter system or something is happening that is much faster than I can actually read it. Let's assume, or maybe my processor or my system on this side in here that is connected to the receiver end is busy doing something else. It's not ready to receive the data. So it just basically accumulates it in the FIFO. Now, when my system is ready, it can just query the empty flag of the FIFO and ask, are you empty? And of course, in this particular situation, the FIFO is not empty. So it will actually have the value 0 in here. Why is it not empty? Because it have this particular data point and this particular data point. And of course it can, because it knows that it's not empty, it will read the particular value in here. And I know that this is because it's a first in or first word fall through, I know that this particular value is valid. And then I read it, I process it, I do whatever I want with it. And then I say, okay, well, my system is going to issue a read UART in here, which just goes to the read enable. And really what it does, it just pushes this out of the FIFO and then puts this at the head. And of course, because I put this in the head, it will be available at the output right away. My empty flag is still 0 because it's not empty. That tells me this particular value is valid still. So my system can process it at its own pace. And let's assume that it processed it. So it'll issue another tick in here. And that tick will tell me, okay, well, now this is done. And of course, this is done. There will be something at the output in here, generally speaking, but the flag that I have in here will be now 1, and my system can query it just to make sure that that value is valid or not. If it's empty, that means that value is not valid. Again, the FIFO is just a way to store data till my system that is receiving is able and capable and ready to actually receive the data. All right, so that was the receiver port or the receiver part. So what about the transmitter part? Well, it's very, very similar. However, it's in the opposite direction. So now my right port, the one that was connected to the receiver, now it's connected to my system, the system that is trying to send something. And of course, if you are the transmitter, your TX should be connected to the RX of another system. So it's complete opposite what happened in here because you're trying to send something. So how do we do that? Well, again, we write to the FIFO whatever we want to actually send, and again we need a FIFO just to make sure that maybe I'm transmitting some data. And remember, the UART is slow. Let's assume that you designed a system that is super fast and generates data really quickly. So what you need to do is first you need to make sure that the FIFO, the sending FIFO, is not full before you actually write into it, just to make sure that you have enough space to do that. All right, so in here, and for some reason for the transmitter, I'm just going to assume that the FIFO might be full because my system might be really quick. In here, I didn't assume that because the receiver, generally speaking, it's receiving at the UART rate, which is slower. But the FIFO in here, I might connect a processor, and that processor might be just doing something really quickly. Anyway, let's say for the sake of argument, I'm actually doing 1101 and then here 000. Okay, and and another one in here. And that's what I want to send. So what I will do is I'll just basically push that value in here, of course, by issuing a write enable in here for 1 tick. I basically push a FIFO word in here. And let's assume that I push another value 1110 and then underscore 0010. Okay, let's assume that these are like my system pushed the first one here in red and pushed the second one in here. Okay, the minute you actually push something and the FIFO is not empty anymore, I would know that the empty flag, which I have in here, will not be 1 anymore. It will be 0 because it's not empty. And of course, after this NOT gate, this will be 1. And what happens for my transmitter, which is just a finite state machine, it will receive that TX starts, indicate that you need to start sending something. And we know that the FIFO actually just places this here at its output, okay, because it's a first word fall through. All right, so what happens is that the following happens. Well, once you get the TX start in here, it will actually go to its TXDN, which is the DN or the data input for the transmitter. It will just push this data into its shift register, and then it will start based on the STIC. It will actually just take this value in here, start pushing it 1 bit at a time, whether from the most significant or the least significant bit, it doesn't matter. What matters is it will push all these 8 data bits out. Once it's done, it will actually do the following. It will actually issue a done tick in here, tells me that I'm done. Of course, that will actually go to the read port of the FIFO, and the read port of the FIFO tells me, okay, now this value is out. What happens is this value is at the head of the FIFO, and of course, if it's at the head of the FIFO, it will be also available at the D out in here. And then, well, is this empty still? No, it's not. So the TX start will be asserted, or is still asserted at that point. So really what's happening is actually this gets pushed in here, all right, and of course after using the STIC we'll push it out to the RX, and it will issue this particular done tick in here, or basically I'm done. So what it tells it tells the FIFO, okay, now you're done with this one, and of course the FIFO at this point is empty, so this will be this will take, or this empty flag will actually be raised to tell me that it's actually 1, and of course this will be 0, and my finite state machine, which takes that start as 0, will stop sending anything. But anyway, the bottom line is what we did is we send a couple of data words to the outside world this way. All right, so let's take a look at the construction or the top file in Verilog for this particular system. And as you might expect, it's just some connecting different components. Even though we still don't know what a receiver or transmitter yet, we'll see it later, but we know that we need to instantiate something. So the UART modules I have in here, I made it parameterized, and it takes a couple of parameters in here. So before I dig deeper into the different code parts in here, so these parameters means D bits are data bits. So in my diagram, I assumed that my receiver and transmitter actually sends 8-bit at a time, but as you might recall from talking about the UART itself, the standard doesn't specify that it has to be 8-bit. It could be it could be, I believe, 5, 6, or 7. Well, 5, 6, 7, or 8 bits. I forgot. But anyway, what I'm trying to say in here, it's parameterized. In my diagram, I'm showing you 8, but really I should just use D bits. All right, and then the second parameter is SB, which stands for stop bit ticks. So in here, we never actually, when I talked about the receiver and the transmitter, I never talked about the stop bits or the start bit, but the receiver and the transmitter both read and generate the start and stop bits. And it will need to know my stop bits. So if I say it's 16, that means I'm using basically one bit for that, not 1.5 or 2 bits. Remember, the stop bit can be 1.5, 1, or 2. Okay, 1, 1.5, or 2. Anyway, we go in, and of course these are the inputs and outputs, and these are the inputs or the outputs of the port. If I actually just surround my module with these particular, or with this particular line, you'll see it. Of course, this means that whenever you need a UART, all you have to do is just take this part and just plug it into your system, and you will have to know that the read port in here actually is the receiver part, and this one here is the send part. So if you need to send something, you deal with it as if you dealt with the FIFO, and it will take care of the RX and the TX. These are connected to the outside world or to the second system that you're trying to communicate with. So you'll see that what I did in my code is I basically separated my inputs and outputs to the receiver port, the transmitter port, and the baud rate generator. So basically I said this is one part, this is one part, and this is another part. All right, this is the timer value, the timer final value. It's for the timer input. Now let's take a look at what the code entails. It's actually just going to instantiate a timer input. It's the same timer input we've seen before. I'm going to tell it how many bits. I decided that it's 11, and we'll see it later because it's the final timer value or the maximum UART. These baud rates are kind of standard. They have certain values. So I based my number of bits based on the final value that I might get if I select maybe the slowest rate or something like that. anyway, or fastest rate, I don't recall, but anyway, 11 bits is enough. And then what we have is, this is what we had at this point. Then we have a receiver. Okay, the receiver will have a receiver. Okay, and then I called it UART RX. This is just a finite state machine, and it takes the inputs and outputs exactly what you see in the diagram. And then I have a FIFO. I'll show you how the FIFO is constructed, but shortly. And then the transmitter in here, okay, that's the transmitter. I have a UARTX. It's a finite state machine. We're going to see how it's constructed. And then another instance of the same FIFO generator. Well, how do I get that FIFO generator? Well, we've seen it in a separate video, and I walked you through some sort of a wizard. I said, like, let's take a look at the IP catalog, and let's say, well, we need a FIFO generator, and then I double click on that, and what I did is basically I walked you through how you can construct a FIFO. So of course it was FIFO generator 0. Just because I'm doing it again, it just gave it the name 1. I called it, well, I needed a native common clock VRAM, and then I went to the VRAM and I said I don't want the standard one, I want the first word fall through. And then I said the write and the read port should be 8 by 8. Basically I'm reading 8 and taking 8 out. And I decided to make each one of these FIFOs 1024. It's not too bad. It's large enough, and I think it's fine. And that's pretty much it. All I have to do is just click OK. And whenever I clicked OK, you go to my resources. There's a lot of files in here, but you'll see something like this in here, which is FIFO generator 0. It's just because I instantiated them here. They have these names. I went to IP source, and then from IP source, I went to instantiating templates, and then in here, I went there and I took that instance in here, or that template, and I basically plugged it in wherever I needed it. That's it. Of course, I formatted it and tabbed it and did all sorts of things, but that's pretty much it. Of course, you don't have to go through this IP catalog thing. I provided an XIC file. Okay, that XIC file, like if you imported, for example, if you go to this hierarchy and you say, well, I need a new design source, and you actually go and you say add a file, and you find the XIC file, you can see that the design source files could be anything. One of them is an XIC somewhere, or XCI, sorry. That's basically one of these, like if I instantiated something, or if I created something using an IP catalog, you can just use that. So you can just import it without going through the wizard yourself. I went through it, and it will appear exactly in the same way.